about a single real-world event. We often describe it using hundreds of different data points. But the truth is, most of those details are just repeating the exact same story. Take a simple dataset of handwritten digits, where each image is just a 16 by 16 pixel grid. To a computer, every single pixel is a unique variable. That forces the machine to navigate 256 different dimensions simultaneously. Processing 256 dimensions is a computational nightmare. It spikes processing costs, consumes massive amounts of memory, and breaks our human ability to visualize the geometry of the data. We are drowning in data, but much of it is perfectly redundant noise. That redundancy hides the actual signal from both us and the machines trying to learn from it. To separate the signal from the noise, let's look at a sample group of bears. If every bear we measure is exactly 6 feet tall, but their weights range from 300 to 800 pounds, measuring their height tells us absolutely nothing new. The height dimension is useless. This scatter plot shows exactly that dynamic. The data points are perfectly aligned horizontally, but widely spread out along the vertical axis. In statistics, a dimension with zero variance provides no new information. It can be safely ignored. Our mathematical goal is to scale that logic up. We need a programmatic way to collapse massive datasets down to fewer dimensions, without losing the underlying story hidden in the numbers. We need an algorithm capable of automatically identifying and deleting those redundant dimensions, preserving only the critical information. That algorithm is Principal Component Analysis, or PCA. It is a spatial solution to the high dimensionality problem. PCA operates on specific logic. It equates the concept of variance directly with the concept of information. The more a feature varies, the more valuable it is. Look at this 3D cloud of data points. PCA hunts to find the direction where points are most widely spread out. We define this specific line as the first principal component. The second direction of maximum variance must be orthogonal, intersecting at a 90-degree angle. By locking onto these orthogonal axes, PCA captures the exact geometric shape of the reality hidden inside the chaotic noise. To execute this reduction in code, it only takes a single line. We instruct the machine to fit and transform the data down to exactly 2 components. This illustrates what deep learning researcher Ian Goodfellow calls the pancake concept. The algorithm structurally rotates the high-dimensional data, so we look directly at its widest, flattest angle. Then comes the squash. We project the data flat onto a lower dimensional plane, permanently removing the depth. Because we discarded that depth, this output is a form of lossy compression. We sacrificed some absolute precision, but we maintained the greatest overall variance of the original dataset. We successfully traded a tiny fraction of accuracy for a massive leap in computational efficiency and human comprehension. Here is the resulting 2D scatterplot. That massive 256-dimensional handwritten digits dataset is now successfully squashed into a clean, readable format. Thanks to PCA, we can finally see the natural clusters of the data with our own eyes. But there is a catch to this mathematical trick. These new principal components are complex mashups of the original features, which destroys our ability to easily label them. We have a beautifully clear map, but the axes no longer translate directly to real-world human terms, like pixel density or bear weight. This leads to the cardinal sin of PCA, blindly reducing dimensions without checking the retained variance, which mathematicians measure using values called eigenvalues. If you force a complex dataset into 2 dimensions, but those 2 dimensions only capture 15% of the total variance, you haven't summarized the story. You've shredded the book. This graphic maps the bias feedback loop. Notice the flow of historical bias into the data and algorithm stages. PCA only hunts for variance. It doesn't judge. If your data contains historical bias, PCA compresses and amplifies that bias directly into your core components. The golden rule of dimensionality reduction is simple. Fewer shelves, same story. PCA gave us a beautifully structured 2D map of our data points, but right now they are just floating there, completely unlabeled. Nobody actually told the algorithm how those clusters should be grouped. We'll need a different set of math for that.